So here in this particular problem, we have a system of three blocks, M1, M2, and M3 from left to right there. M1 here is 2 kilogram, M2 is 9 kilograms, and then M3 is 2.5 kilograms. And they all sit across a rough surface, which the coefficient of kinetic friction is given to us as 0.1. Alright, so if you need to, pause the video, read the different parts. Let's crack this problem out. Alright. So let's do part A in this one. It asks us to calculate the net force acting on the system. So visually, we have a force F here of 63 newtons as stated in the statement. It's going to push M1, which results push M2 and M3 and so on to the right across this rough surface. Okay. So in order to do so, all we have to do is find the net force, which means account for all the forces. So here we have F pushing right, but I know that I should push right. Because these boxes are sitting on a rough surface, they each will generate a frictional force that's acting against F. So therefore they will be pointing leftward. So here in my work, I have the net force of the system is equal to F subtracted from all the kinetic frictional force of the system. Okay, so here you have three blocks, so therefore there should be three kinetic frictional force acting on each of the boxes. Okay, so let's go and identify all these kinetic frictional force. Here, this first orange arrow is the F of K on block 1, and then here is the F of K on block 2. I've drawn the vector here a little longer because it does have more mass. So because it has more mass, it will press down on the floor a little more, so it does create a little bit more friction. So not drawing a scale, but at least to help you identify what should be more and what should be less. And then 2.5 here, it's a little longer than the 2 kilogram because it is 2.5. Okay, so there is a kinetic frictional force here acting on this 2.5 kilogram block as well. So I'm going to call that FK3. So I'm just going to use a subscript based on the mass. So I have FK1, FK2, and FK3. Well, and that's the case. All I'm just going to do is plug in F as 63 newtons. I'm going to subtract it FK1, F of K2, and F of K3. The reason I'm subtracting is because F of K1, 2, and 3 is acting against the system's motion. So the three blocks wants to move rightward, but F of K is, in this particular problem, is going to oppose that, which means they would have to be pointing left, and left would indicate that these vectors are negative. Okay, so I've already accounted for the negative sign in my work at this particular step here. So pay attention to that later on. Here, I'm just going to go ahead and carry the 63 newtons down. But I know that by definition, the kinetic frictional force is the coefficient of friction times the normal force acting on each of the boxes. Okay, so here I've expanded F of K simply to mu K F of N, and I've carried down the subscript for each of the mass. So here's M1, and then FK2 is simply mu K times F of N2, and then F of K3 is simply mu K F of N3. So you notice here the mu K does not have a coefficient because the coefficient is the same for all three blocks, okay? For this problem anyways. All right. Therefore, I can go ahead and factor out a coefficient of kinetic friction here in this particular next step. You don't have to, but I'm just going to factor it out just for visual purposes in case you have to derive functions in your work. So here's mu K, that term has mu K, that term has mu K. So all three of these terms has a mu K, so I'm going to pull that out and want to factor it. But you have to be careful here with signs when you factor stuff out. So here's the negative sign in front. So therefore, all these signs in here have to be plus because you need to distribute the negative sign back into later so that it matches with these signs in the third line here. So all these are negatives. So therefore, when you factor out, because there's a negative in the front already, you have to make sure these signs are correct. Otherwise, your algebra is going to be off. Okay. So let's do that, and then in order to find what Fn1, Fn2, Fn3 is, you have to go to the diagram and draw your free body diagram. So the first vector red that can't come or that appeared here on the screen is the weight of the first box. So here the weight of the first box I've called Fg1, and the weight by definition is just mass times gravity at the surface of the planet. So here is m1 times g. But that, for this particular problem, is your normal force because your normal force is opposing the weight of the box. So in this case, that's F of 1 pointing upward. Okay, here is F of G2. Again, I've drawn F of G2 just a little longer, just for the sake of visual. This is 9 kilogram compared to 2, so the weight should be more. And then if that's the case, f of n should be the same magnitude, just in the opposite direction of f of g2. Therefore, this vector here is f of n2. So we can say that f of n2 is the same magnitude as f of g2. And so on for m3. So m3 has its own weight, f of g3. But if it's f of g3, then it's m3 times g. But that's the weight keeping it on the surface. At the same time, the surface is going to push onto the box with the same magnitude. So this is your normal force for m3. So really, same concept, just applied 3 different times, okay? So in that case, we know what each of these f of n1, 2, and 3 are equal to, so we can just go ahead and do a quick substitution. So I've carried my work down, but instead of fn1, I'm just going to replace that for this problem with m1g because it does equal in magnitude, all right? And so on with fn2 and fn3. So I've just replaced each of these fn's with the weight of each of the mass for this particular problem because it is a true statement. Therefore, I can factor out m's here. Here's an m1, m2, and m3. All these terms in the parentheses have a g, so I'm just going to factor that g out. Therefore, I can just go ahead and plug values in now. Okay, the coefficient of kinetic friction is 0.1. M1 is 2. M2 is 9. M3 is 2.5. So if you add all those values of m's together, you should get 13.5 kilograms. And I highlighted here the g. You notice here my substitution for g is a positive 9.8 meters per second square. That's important to keep in mind because in my second line here, I've already accounted for the negative signs. So it's important that you don't plug in a negative value here in your work. Otherwise, again, you're going to get a different value, okay? So make sure you do that properly. Don't plug in a negative sign here because it's already been accounted for. All right, other than that, if you do the math, it'll be 63 newtons minus 13.23 newtons. And then if you do that on your calculator, you should get a value for 9.77 newtons. And here, I include the plus sign because in part A, it has to find the net force. Well, the net force is a vector, and it didn't use the word magnitude, so I'm going to include a plus sign here because the system will be pushed to the right. So, aka the net force has to follow that direction, so it's going to be positive. Okay, so the answer for part A is going to be plus 49.77 newtons. That's it. Let's go ahead and crack out part B. Part B asks us to find the net force on M1. M1 here is the first box on the left, which is 2 kilograms. So I'll show you how to do this a couple of different ways here. Pick one that you like. Net force on M1 is simply mass times acceleration. And since the part B asks us to find the net force on M1, I will use just mass 1. Okay. Therefore, we know what mass 1 is. Mass 1 is in the diagram, which is 2 kilograms. However, what I don't know is the acceleration system. I haven't found it yet, but that's super easy to do. We already found our net force, right? Our net force is calculated in the previous part A. We know the total mass is 13.5 kilograms simply by adding 2, 9, and 2.5. The only thing missing here is really AX, but we can find that. So therefore, let's crack it out. The net force of the system that we just found in part A is 49.77 newtons. The total mass, by adding all the masses up, is 13.5. So therefore, to find AX, we just have to divide both sides by 13.5. Here, hold on, excuse me, let me just do this properly. Since I divide that, I totally forgot to delete those values, okay? Alright, so therefore, okay, if you do that correctly, the acceleration should come out to be 3.69 meters per second square. And once you do that, you can just substitute in for AX. So therefore, I carry my second line down here. The net force on M1 is simply 2 kilograms times the acceleration I just calculated, which is 3.69 meters per second square. And then the calculator work is going to give us a value of 7.38 newtons. Okay. And here, I've also included the plus sign because I'm reading part B and it says just find the net force. It did not specify the magnitude, so I do need to include the direction for that. So the net force acting on M1 is 7.38 newtons, right word or plus sign, east if you like. All right, so that's that. Part B can also be found using percentages, or I like to do mass percentage. Okay, the net force on M1 is equal to the percentage of M1 divided by the total mass of the system times the net force. So the way you should try to look at this is M1 is 2 kilograms. So it makes up 2 parts of 13.5 kilograms. Okay, so the whole system is only 13.5 kilograms, but the first block occupies 2 of those kilograms. So therefore, it's gonna absorb, it's gonna occupy, it's gonna take up a certain percentage, right, of the net force of the system. So here's M1, that's divided by the total. That gives you a percentage of the system, and then percentage of what the total force in the system. All right, so if you plug values in, M1 here is 2 kilograms, the total mass is 13.5, and then the net force on the system is 49.77 that we calculated in part A. So as you can see, if you do this correctly, it comes out to be 7.37, which is pretty much the same answer as 7.38. There's some decimals involved here, so there's a little bit of rounding error. But as you can see, 7.38, 7.37, it's the same thing. All right, so pick a method that you like, and as long as you can use the information that you calculated, hopefully it works out. Part C asks us to calculate the net force on M2, the middle block here of the 9 kilograms. So I'm just going to go ahead and crack this out as well, using the same approach as I did in part B. So here I have the net force of M2, and if it's M2, then I have to use M2 on the right side. AX does not have a subscript of number because the acceleration is the same for all the blocks. Therefore, M2 is 9 kilogram, as shown here in the middle, and the acceleration we calculated in the previous slide is 3.69 meters per second square. And if you do that, you should get a net force for M2, just for the middle block, of 33.21 newtons. Okay, so that's our answer for part C. Again, if you want to do percentages for the middle block is 9 of 13.5 parts. So M2 here is 9 kilogram, the total mass is 13.5. So therefore, if you do a percentage of the whole, so to me, the net force of the system is the whole. Okay, so therefore, you should get the same value. So if you plug in 9 for M2, divided by the total mass of the system, and then the whole net force, or just net force acting on the system, which already account for frictional force, is a result of 49.77, and you should get the same value. Here is 33.18 newtons. Up here I got 33.21. As you can see, the difference is 0.03, give take, rounding errors. Yeah. All right, let's do part D. Part D here asks us to find the magnitude of F32 exerted on the 9 kilogram block by the 2.5 kilogram block. As I stated earlier, the 9 kilogram is going to want to go right, but the 2.5 kilogram here on the right is going to, get in the way. Okay, so I'm just going to go ahead and draw these vectors here, the contact force or the normal force between M2 and M3. Here, the first arrow, I'm going to call the F32. This is the force exerted by block 3 onto 2. But at the same time, I know that for these types of problems, there is an equal and opposite contact force, or normal force, if you like to call it. Therefore, this is F2 exerted onto 3. So why the question asks you to find the magnitude of F32, I'm actually going to find F23 because I know they're the same value. So when it gets to this type of questions, it's up to you to decide which box you look at. So even though it asks for F32, I'm actually going to find F23 by looking at box 3. Okay. The reason I'm looking at box 3 is because it has the least amount of horizontal force acting on it. So what's causing M3 to move? It's F23. But what's slowing it down is FK3. So there are only 2 vectors that I need to account for in the horizontal direction. So one, again, F23 is going to cause M3 to move to the right. But as it moves to the right, there is friction against it, which is FK3. So that's 1 arrow to the right, 1 arrow to the left. It has the least amount of arrows to deal with. So I'm going to go ahead and use M3 to find F23. But F23 is the same as F32. Okay, so I'm going to focus my attention here on box 3. So I'm just going to set up the physics for box 3. Therefore, the net force on M3 is just M3 times AX. But the net force on M3 in this case, well, what's causing M3 to move to the right is F by box 2 onto box 3. I'm going to subtract it by F of K3, and that equals the mass 3 times acceleration. And then to solve for F of 3, I need to isolate for it. In order to isolate for it, I need to move this negative FK3 to the right side of the equal sign, which causes it to change sign. So here's negative. When you move it, it becomes positive. So therefore, here I have a bunch of values already. M3 I know is 2.5. Acceleration has been the same for the whole entire presentation, which is 3.69 that we calculated earlier. Here I broke up f of k3 into mu k f of n3, but from the diagram, again, we know that f of k is mu k f of n3, but we know that f of n3 is just the weight of the third block. Okay. All right. Other than that, let's go ahead and plug values in. Mu k is 0.1. Fn, again, it's just the weight of the third block, which is m3 times g. So m3 is just 2.5 kilogram, and then g, once again, I already counted for the negative sign earlier, so I'm just going to plug in 9.8 here rather than negative 9.8. So it's important that you keep track of my work. I like to introduce negative signs right away, so when I plug in values, they're just all positive. Okay, so if you do that correctly, the magnitude of F23 is 11.675 newtons. But as I stated earlier, the question specifically asked for the magnitude of F32. But I know that if I solve for F23, it is the same magnitude as F32. So here, I just wrote the statement for you if you like. F23 is the same as F32. So I know the answer is still 11.675 newtons. And here, there's no direction because I see the word magnitude in part D. Other than that, that is it for this particular presentation. Okay? All right. Stay nerdy. I hope that helps. Don't be whack.